In the summer of 1940, at the Royal Air Force's Hornchurch Airfield in Essex, a pivotal demonstration unfolded. Two Supermarine Spitfires, visually indistinguishable, stood poised on the concrete tarmac. Both aircraft were powered by the identical Merlin engine, equipped with the same formidable 8-gun armament, and had the same skilled pilot securely fastened within their cockpits. The stage was set for a comparison that would help define the future of aerial combat. Squadron leader Desmond Cook initiated the sequence by bringing the first aircraft to full power. Its takeoff run spanned 320 yards, and it ascended to an altitude of 20,000 feet in 11 minutes and 8 seconds. The Spitfire's maximum operational height, its service ceiling, where the rarefied atmosphere caused engines to strain, was recorded at 32,000 feet. Following a brief interval of 20 minutes, Cook then entered the second Spitfire. This aircraft featured an identical airframe and engine, yet it distinguished itself with a different propeller assembly. The performance metrics were strikingly divergent. Its takeoff run was a mere 225 yards, its ascent to 20,000 feet was accomplished in a swift 7 minutes and 42 seconds, and its service ceiling soared to an impressive 39,000 feet, showcasing a profound enhancement in aeronautical capability. The very same aircraft model, housing the identical power plant, was now demonstrating radically different operational capabilities at a time when the fate of a global conflict teetered precariously. The critical distinction between achieving triumph and succumbing to defeat in the fierce aerial engagements of the Battle of Britain was ultimately determined by a trio of rapidly rotating aluminum blades. This innovative propeller design, which aeronautical specialists across the United States had dismissed as excessively intricate and impractical, was the brainchild of Frank Caldwell. It was the very invention projected to enable American bombers to achieve speeds 100 mph faster, and its profound efficacy had just been unequivocally demonstrated over the bucolic English landscape. However, the compelling narrative of how one steadfast engineer's quantitative evidence defied the entrenched assumptions of an entire industrial sector commenced 8 years prior, within the confines of a manufacturing plant, where the prevailing sentiment declared his concept utterly unworkable. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Frank Walker Caldwell found himself in the oil-stained testing facility of the Hamilton Standard Propeller Corporation in East Hartford, Connecticut, on a somber February morning in 1932. At 43 years of age, this mechanical engineer, a distinguished alumnus of MIT, exuded the deliberate composure of an individual whose conviction rested firmly on empirical data rather than subjective opinions. A pair of wire-rimmed spectacles sat precisely upon his nose, and a clipboard was an ever-present fixture in his well-worn hands. Positioned directly behind him, secured to a test stand that vibrated with intense mechanical energy, spun a lustrous metal propeller, unlike anything previously conceived in the annals of aviation. It featured 3 aluminum blades, each possessing the remarkable ability to alter its angle while continuously rotating at an astonishing rate of 2,400 revolutions per minute. The pivotal telephone communication that would irrevocably alter the trajectory of his work had been received merely 3 days prior from Boeing Field in Seattle. The Boeing Model 247 heralded as America's groundbreaking new airliner, lay immobilized at Denver Municipal Airport, presenting a lamentable sight akin to a pedigreed racehorse hobbled by injury. At an elevation of 5,280 feet, this twin-engine marvel, designed to transport passengers across the continent in unprecedented time, found itself struggling immensely to surmount the formidable Rocky Mountains. Its predicament stemmed from two wooden propeller blades, fixed at a singular pitch angle. While optimized for a specific flight condition, this configuration rendered the aircraft virtually ineffectual under all other circumstances. Pan American Airways. President Juan Trippe had issued a stark ultimatum to Boeing that very morning. Rectify this issue, or we shall acquire aircraft from Douglas. The stakes could not have been more critical. United Airlines had placed an order for 25 Model 247s, and TWA was contemplating a purchase of 30. Yet, all these promising prospects would dissipate if the world's most technologically advanced airliner proved incapable of traversing a mountain range. Caldwell was no stranger to such resistance and skepticism. Throughout the American aviation community, the prevailing conventional wisdom circulated like an irrefutable doctrine, permeating discussions from aircraft hangars to corporate boardrooms. Variable pitch propellers were perceived as an elaborate solution in search of a non-existent problem. Critics argued they were excessively weighty for any marginal performance enhancement, overly intricate for reliable operation, and comprised too many precisely machined, moving components functioning in a hostile operational environment where lubricating oil could freeze at high altitudes and incessant vibration could dismantle delicate mechanisms. The Army Air Corps Engineering Division had, in an official pronouncement, deemed Caldwell's hydraulic design to be mechanically unsound. Even Charles Lindbergh, arguably the most venerated figure in aviation, had expressed reservations about the concept during a private discussion held at Wright Field the preceding autumn. Nevertheless, Caldwell possessed the quiet, unwavering self-assurance of an engineer whose predictions had been vindicated on numerous prior occasions. Serving as the government's chief propeller engineer from 1917 to 1928, he had observed aviation specialists initially resist the adoption of metal propellers, citing the perceived lightness of wood, and subsequently oppose ground-adjustable propellers due to concerns about unnecessary complexity. Each instance, his meticulously compiled data had systematically dismantled their entrenched assumptions. And each instance, the industry had in due course followed the path illuminated by his rigorous numerical analyses. This particular juncture, however, carried a distinct weight. This time, the very careers of individuals and the solvency of entire corporations hung precariously in the balance. Hamilton Standard had committed substantial resources to Caldwell's groundbreaking design, encompassing the livelihoods of 800 employees in East Hartford, in addition to extensive manufacturing contracts that spanned from the eastern seaboard of Connecticut to the western reaches of California. The venerable company, renowned for crafting the propellers that powered Lindbergh's iconic Spirit of St. Louis, faced the dire prospect of its demise if Caldwell's intricate calculations proved erroneous. His own esteemed reputation, meticulously forged over a quarter-century of dedicated propeller development, now depended entirely upon 3 rotating blades and an innovative hydraulic governor system. This sophisticated mechanism ingeniously utilized engine oil pressure to autonomously regulate the blade angle in response to prevailing flight conditions. The underlying engineering was remarkably elegant in its simplicity and effectiveness. During critical phases, such as takeoff and initial climb, when the demand for maximum power was paramount, the propeller automatically transitioned to a fine pitch setting, akin to a vehicle engaging a low gear. This allowed the engine to achieve higher rotational speeds and consequently generate optimal thrust. Upon reaching cruising altitude, the system seamlessly shifted to a coarser pitch, thereby maximizing forward speed and enhancing fuel efficiency. Furthermore, in the unfortunate event of an engine failure, the propeller possessed the critical capability to feather its blades, aligning them parallel to the airflow. This action effectively eliminated aerodynamic drag that would otherwise imperil the aircraft, potentially inducing a catastrophic, uncontrolled spiral. The numerical evidence resonated with irrefutable mathematical certainty. Caldwell's extensive wind tunnel experiments conducted at MIT had conclusively demonstrated that constant-speed propellers possessed the capacity to augment climb rates by a remarkable 40%, extend the service ceiling by an additional 7,000 feet, and improve fuel efficiency by 15% across the entire spectrum of flight regimes. Yet, these compelling figures held little sway if the broader aviation industry remained unconvinced and unwilling to embrace their implications. The decisive breakthrough arrived on February 15, 1933, when Pat Patterson, the president of United Airlines, extended a final opportunity to Hamilton Standard. This entailed one conclusive test flight, with their purportedly impossible propeller seamlessly integrated into a Boeing 247. Test pilot Eddie Allen, a former Navy aviator renowned for his unflappable demeanor and exceptional skill, was tasked with subjecting Caldwell's theoretical assertions to the ultimate practical examination. The flight was meticulously planned over the very same challenging Rocky Mountain terrain that had rendered identical aircraft grounded just 2 weeks prior. Allen expertly guided the aircraft, steadily ascending past 6,000 feet, the very altitude that had previously thwarted the fixed-pitch 247. He continued his climb, reaching 8,000, then 10,000 feet, ultimately traversing the Continental Divide with an ease that made the formidable mountain range appear no more challenging than a minor undulation on a country road. The constant-speed propeller, a marvel of engineering, autonomously adjusted itself to each change in altitude, meticulously maintaining optimal engine RPM while simultaneously maximizing thrust output. In stark contrast to the fixed-pitch aircraft, which had struggled profoundly to even attain 6,000 feet over Denver, the modified 247 achieved an impressive service ceiling of 20,700 feet. The enhancement in cruise speed proved equally remarkable, demonstrating an increase of 15 meter weft across all altitudes, coupled with a notable 12% improvement in fuel efficiency when operating at normal cruise power settings. Cruise power settings. That evening, Patterson was informed of the test outcomes via telegram, which unequivocally stated, "Constant speed propeller exceeds all performance claims. Recommend immediate adoption for entire United Fleet." As manufacturing requests swiftly inundated Hamilton Standard's East Hartford plant, a grim global situation was simultaneously unfolding. In Germany, the National Socialist Party had aggressively seized control of the government, while in Japan, military leaders openly articulated their intentions for expansion across the Pacific. The ominous specter of war was rapidly materializing over both Europe and Asia, and this groundbreaking propeller technology, initially conceived to enhance the comfort of airline passengers, was poised to transform into a critical strategic asset for the United States. On a warm and muggy May day in 1933, the telephone rang in Caldwell's office. The individual on the other end introduced himself as Commander John Towers, representing the Navy Department's Bureau of Aeronautics. Their urgent requirement was to discuss advanced combat aircraft, specifically swift fighter planes capable of superior climbing and maneuvering performance to outclass any aircraft being developed by the Germans or Japanese, alongside formidable bombers that could attain greater altitudes and speeds than any enemy interceptors could possibly reach. The era of aerial combat was drawing near, and Frank Caldwell possessed the crucial innovation that would ultimately ensure American dominance in the skies. A pivotal telegram arrived at the Hamilton Standard facility on November 13, 1933, delivering news that conclusively vindicated every principle Frank Caldwell had tirelessly striven to establish. The National Aeronautic Association formally declared Hamilton Standard Propeller Corporation as the recipient of the prestigious Collier Trophy, widely acknowledged as the paramount accolade in the field of aviation, specifically recognizing the development of a controllable pitch propeller with particular credit to Frank W. Caldwell. Following this esteemed recognition, President Franklin Roosevelt himself was scheduled to extend his personal congratulations to Caldwell during an official ceremony at the White House in December. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. Yet, even as numerous photographers documented Caldwell's handshake with the president, a significant segment of the established aviation community maintained an unyielding skepticism. At Wright Field in Dayton, Ohio, Army test pilots voiced considerable displeasure regarding the added intricacy that constant-speed propellers introduced into military aircraft. Major Benjamin Kelsey, who headed the Army Air Corps Fighter Projects Office, articulated concerns that resonated deeply within military hangars nationwide. What happens when that hydraulic system fails over Germany? When oil pressure drops and the propeller locks up, fixed-pitch props don't break down because there's nothing to break. Caldwell's approach to these objections was, as usual, systematically organized. If military aviators insisted on unequivocal evidence of reliability under genuine combat scenarios, he was determined to furnish them with comprehensive data that would dispel any lingering doubts. Dedicating 18-hour workdays within Hamilton Standard's significantly enlarged testing complex, he pioneered what would become known as the whirl test. This innovative method involved rigidly mounting propellers onto fixed stands to meticulously gauge their thrust, operational endurance, rotational speed, and structural integrity under extraordinarily harsh conditions that far surpassed anything an aircraft would encounter in actual wartime operations. The underlying technical advancement that rendered all these capabilities feasible was remarkable for its elegant mechanical straightforwardness. Caldwell's groundbreaking hydromatic propeller harnessed the engine's inherent oil pressure to actuate a piston, which in turn altered the blade angle through an intricate yet reliable arrangement of gears and counterweights. A compact centrifugal governor, no larger in diameter than a standard coffee can, meticulously regulated and sustained a constant engine RPM irrespective of varying flight conditions, achieving this by automatically adjusting the propeller's blade pitch. When an aircraft ascended and atmospheric density diminished, the propeller intuitively transitioned to a fine pitch, a configuration akin to a low gear in automotive terms, to preserve engine RPM and maximize available power. Conversely, during steady cruise flight, the system shifted to a coarse pitch, optimizing for peak speed and superior fuel economy. Should the engine RPM surge excessively during a steep dive, the propeller would automatically coarsen its pitch, effectively preventing any potential damage from overspeeding. Perhaps the most revolutionary attribute was the propeller's feathering capability. In the event of a complete engine failure, oil pressure supplied by the remaining operational engines could be directed to rotate the blades of the defunct propeller until they were aligned parallel to the prevailing airflow. This crucial action effectively nullified the immense aerodynamic drag that would otherwise inevitably pull a multi-engine aircraft into an uncontrollable, perilous spiral. For bomber crews embarking on missions deep within hostile airspace, this singular design feature could profoundly determine the outcome, representing the critical difference between successfully returning to base on operational engines or tragically becoming another casualty statistic of the conflict. The enhancements in performance were indisputable when directly translated into tangible combat readiness. A comprehensive comparison between a P-51 Mustang, outfitted with Caldwell's advanced constant-speed propeller, and an identical aircraft utilizing conventional fixed-pitch blades revealed stark and dramatic disparities across every operational flight parameter. Takeoff distances were significantly reduced by 30%, which enabled fighter squadrons to deploy rapidly from shorter, more forward airfields closer to the front lines. The rate of climb experienced a substantial 40% increase, shaving invaluable minutes off the time required for aircraft to reach optimal intercept altitudes. The service ceiling soared by an impressive 7,000 feet, granting American fighters a critical altitude advantage over their adversaries. Furthermore, combat range was extended by an additional 200 miles, and overall fuel efficiency saw a commendable 15% improvement across the entire spectrum of power settings. However, mere figures on laboratory test reports held little significance if the propellers were to malfunction precisely when pilots depended on them most critically. Caldwell's relentless pursuit of absolute reliability compelled him to subject every single component to testing far beyond its intended operational thresholds. Propeller blades, for instance, were exposed to structural loads that were 50% greater than the maximum stress anticipated during intense combat. Hydraulic governors were made to operate continuously for a grueling 500 hours under extreme temperature variations, ranging from a frigid 40 degrees below zero to a scorching 160 degrees Fahrenheit. Oil seals underwent rigorous evaluations using contaminants specifically designed to mimic the effects of battle damage and the consequences of neglected maintenance. As Hamilton Standard's order books rapidly filled with lucrative military contracts, the opposition from long-established aviation manufacturers became increasingly vocal and pronounced. Curtiss Wright, a prominent manufacturer specializing in fixed-pitch propellers for the majority of Army Air Corps fighters, initiated an aggressive lobbying campaign. They vociferously argued that constant-speed propellers represented an unnecessary layer of complexity that would ultimately jeopardize the lives of American pilots. Their chief engineer, Dr. George Meade, authored and published several technical papers that directly challenged the feasibility of hydraulic systems operating dependably at combat altitudes, where ambient temperatures plummeted to 60 degrees below zero and oil viscosity dramatically increased. Caldwell's rebuttal was as always, grounded in irrefutable data. His extensive cold weather tests conducted at 35,000 feet unequivocally demonstrated that the hydromatic system, contrary to popular belief, actually performed more effectively at high altitudes because the increased oil viscosity facilitated a more precise and positive pressure control. Furthermore, comprehensive vibration tests revealed that constant-speed propellers experienced fewer mechanical failures compared to their fixed-pitch counterparts. This superior resilience was attributed to the automatic pitch adjustment mechanism, which effectively eliminated the specific resonance frequencies known to cause stress fractures in propeller hubs and loosen critical mounting bolts. The pivotal moment in the advancement of aviation technology unfolded during a compelling demonstration at Selfridge Field in Michigan on March 21, 1934. In a meticulously controlled experiment designed to showcase the new innovation, two P-26 fighter aircraft, identical in every respect, launched into the sky simultaneously. One of these formidable machines was equipped with the conventional fixed-pitch propeller, a standard of the era, while its counterpart featured Frank Caldwell's revolutionary constant-speed system. The disparity in their aerial performance was so remarkably pronounced that seasoned pilots observing the spectacle initially harbored suspicions that the constant-speed aircraft must have been secretly fitted with a substantially more powerful engine. The raw figures dramatically underscored this difference. The time required to ascend to an altitude of 10,000 feet was a painstaking 8 minutes and 30 seconds for the fixed-pitch fighter, yet a swift 5 minutes and 40 seconds for the version utilizing the constant speed mechanism. Furthermore, at an altitude of 15,000 feet, the maximum speed achieved by the traditional aircraft was 187 nm, whereas the technologically superior model soared at 203. The service ceiling, representing the maximum operational altitude, saw an equally significant leap from 28,000 feet to an impressive 34,500 feet. That very evening, Lieutenant Colonel Carl Spaatz, a highly respected officer whose distinguished career would later see him assume command of all American strategic air forces operating in Europe, meticulously drafted a report. His findings were unequivocally clear. He strongly advocated for the immediate and widespread adoption of constant-speed propellers across the entire fleet of Army Air Corps fighters and bombers. In his compelling report, he asserted with conviction, "The performance advantage is so significant that it represents a fundamental shift in combat capability. Any air force equipped with constant-speed propellers will possess decisive superiority over opponents using fixed-pitch systems." His words carried immense weight, highlighting the transformative potential of Caldwell's invention to fundamentally alter the dynamics of aerial warfare. As the year 1934 drew to a close, the manufacturing facilities of Hamilton Standard hummed with ceaseless activity, their production lines operating around the clock to fulfill an burgeoning demand. Orders poured in, not only from the United States Army and Navy, but also from a growing number of civilian airlines, all eager to capitalize on the demonstrable advantages of the constant-speed propeller. Yet concurrently, across the vast expanse of the Atlantic Ocean, a more ominous narrative was beginning to unfold. Darker geopolitical events were stirring, events that would soon plunge the world into conflict and subject Caldwell's ingenious innovation to trials under circumstances far more perilous than any peacetime engineer could possibly in vision. While Frank Caldwell meticulously refined his sophisticated propeller designs in the quiet workshops of Connecticut, European aircraft manufacturers found themselves dangerously lagging in the race for technological supremacy. For instance, within the expansive Messerschmitt factories nestled outside Augsburg, Germany's most advanced fighter aircraft, the formidable Bf-109, still relied upon manually adjustable propellers. This archaic system compelled pilots to constantly manipulate cumbersome pitch levers, a critical distraction during the intense exigencies of aerial combat. Similarly, iconic British fighters, such as the Supermarine Spitfire and the Hawker Hurricane, were equipped with rudimentary two-position propellers. These offered only a coarse pitch setting for high-speed flight or a fine pitch for climbing, completely devoid of any intermediate adjustments or, crucially, any automatic adjustment capabilities, leaving their pilots at a distinct disadvantage. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The grim and deadly ramifications of this stark technological disparity rapidly surfaced during the initial months of the burgeoning conflict. RAF combat reports from September 1939 painted a chilling and unvarnished picture of the skies above Europe, a narrative so alarming it frequently deprived Air Ministry officials of sleep. German Bf-109s, agile and well-equipped, consistently outclimbed their British counterparts, especially above the critical altitude of 15,000 feet. At these heights, the manually adjusted propellers of the Luftwaffe aircraft, despite their operational complexity, paradoxically afforded German pilots a vital, often decisive advantage. Concurrently, RAF bomber crews relayed distressing accounts of missions aborted, their aircraft simply incapable of achieving the necessary altitude to safely clear treacherous mountain ranges like the Alps, or to evade the relentless pursuit of German interceptors. Fighter command pilots, valiantly scrambling to intercept enemy formations, reported losing invaluable seconds during their ascent. These were seconds that frequently delineated the stark difference between successfully engaging enemy bombers before they could reach their designated targets and watching helplessly as German formations receded into the protective shroud of cloud cover. Air Marshal Hugh Dowding, the meticulously methodical Scotsman at the helm of Fighter Command, harbored deep private anxieties. He worried that, in the looming and inevitable battle for air superiority, Britain's fighter fleet was fundamentally outmatched technologically. Intelligence dispatches from France further corroborated these fears, detailing how German pilots possessed the capability to continuously optimize their aircraft's performance throughout an engagement, while their RAF counterparts were burdened by manual pitch controls that demanded constant, diverting attention precisely when their focus should have been exclusively riveted on the adversary. At the prestigious 1938 Society of Automotive Engineers conference held in Detroit, Caldwell presented a trove of data that, in hindsight, should have sent ripples of alarm through every military aviation expert present. His comprehensive comparison of constant speed versus fixed pitch propeller performance, conducted using identical engine configurations, unveiled figures that were nothing short of revolutionary in their implications. The static thrust, representing the raw power available for takeoff, and the initial phase of climb, demonstrated a remarkable 40% increase when coupled with automatic pitch control. The rate of climb, particularly below 10,000 feet, saw an impressive surge of 35%. Furthermore, fuel consumption at crucial cruise altitudes registered a significant 15% reduction. Most profoundly, the combat ceiling, the maximum effective altitude for engagement, expanded by more than 6,000 feet, thereby granting properly equipped fighters an undeniable and decisive altitude advantage over their adversaries. Astonishingly, despite this compelling evidence, many European aviation engineers summarily dismissed these findings as mere theoretical advantages with practical disadvantages that would prove fatal in combat conditions. Dr. Ernst Haenkel, a prominent designer of Germany's most advanced fighters and bombers, publicly articulated his skepticism, arguing that hydraulic propeller systems represented American over-engineering that sacrificed reliability for marginal performance gains. Echoing these sentiments, British propeller manufacturers also staunchly maintained that manually controlled pitch mechanisms actually provided pilots with a more precise and nuanced level of control during complex combat maneuvers. The logistical and technical production challenge confronting Hamilton Standard intensified with each passing month, as military orders rapidly multiplied, creating an ever-escalating demand. Each individual constant-speed propeller was a marvel of engineering, necessitating the precise machining of 47 distinct components, each with tolerances measured in mere thousandths of an inch. The assembly procedures themselves demanded the meticulous skill of highly trained craftsmen, working with specialized tools and adhering to exacting standards. In response to this surging demand, the company's East Hartford factory expanded significantly, transitioning to an exhaustive schedule of 3 shifts operating continuously, 7 days a week. However, even these Herculean efforts proved insufficient, as demand consistently outstripped production capacity. The Army Air Corps, the Navy, and various Allied purchasing commissions found themselves in a fierce competition for the limited output of these critical components. In this high-stakes environment, the relentless pursuit of quality control transformed into both Caldwell's unwavering obsession and his recurring nightmare. A particularly alarming incident occurred when a single batch of faulty governors, which are the critical components responsible for regulating oil pressure and precisely controlling blade pitch, led to the loss of hydraulic pressure in 3 propellers during test flights conducted at Wright Field. These critical failures transpired during simulated combat maneuvers, precisely the high-stress conditions where absolute reliability was paramount. The gravity of these incidents was such that Army Air Corps procurement officers issued a serious threat. They would cancel pending orders valued at a staggering $12 million. Critics throughout the aviation industry swiftly capitalized on these incidents, seizing upon them as irrefutable proof that constant-speed propellers were inherently too complex and fragile for the brutal realities of combat conditions, where, as they argued, simplicity equals survival. Caldwell's resolute response to this crisis vividly showcased the methodical determination and unwavering commitment that had been the driving force throughout his distinguished career. Collaborating intensely with a select team of Hamilton Standard's most brilliant engineers, he spearheaded a complete redesign of the governor system, accomplishing this monumental task in an astonishing 6 weeks. The revised design incorporated crucial enhancements, including redundant pressure circuits and innovative backup mechanical controls. These fail-safes were engineered to ensure that basic propeller function would be maintained even in the catastrophic event of a complete failure of the primary hydraulic system. Furthermore, New, rigorous testing protocols were immediately implemented, subjecting every single propeller to stress levels that exceeded anticipated combat conditions by a demanding 50%. Most significantly, Caldwell personally instituted an uncompromising policy, taking it upon himself to individually inspect and formally sign off on every propeller destined for military customers, a testament to his profound personal accountability and dedication to quality. The enhancements in operational dependability materialized at a truly pivotal juncture. As the early months of 1939 unfolded, the formidable strength of the Luftwaffe had swelled to encompass more than 4,000 aircraft, a stark contrast to RAF Fighter Command, which commanded a mere 700 operational fighters. Concurrently, German aircraft manufacturing was surging forward with remarkable speed, with the proliferation of new production facilities rolling out sophisticated models such as the formidable Bf-109E and the potent twin-engine Bf-110 destroyer aircraft. Intelligence assessments consistently suggested that German bomber fleets possessed both the operational range and the service ceiling necessary to strike any strategic objective across Britain, while the existing RAF fighter fleet frequently found it challenging to engage these high-altitude enemy formations effectively. This gaping technological chasm became grimly evident during the brutal Battle of France. Squadrons of RAF Hurricanes and Spitfires, which were still equipped with rudimentary two-position propellers, routinely discovered themselves being outmaneuvered and surpassed by their German counterparts, particularly at altitudes exceeding 20,000 feet. Flight Lieutenant Douglas Bader, then at the helm of 242 Squadron, provided a stark assessment, observing that German aircraft could climb away from us at will above 15,000 meters. Our propellers simply cannot provide the power needed for sustained high-altitude combat. Consequently, squadron losses accumulated relentlessly as RAF aviators painfully recognized that their aircraft's operational performance envelope was critically deficient when pitted against an adversary that possessed the ability to dictate the terms and location of engagement. By June 1940, with German armies marching inexorably towards the Channel coast and the Luftwaffe poised for an imminent onslaught against Britain, Fighter Command confronted a dire technological predicament that imperiled the very fabric of the entire war effort. The very constant speed propellers that American test pilots had hailed as groundbreaking innovations were conspicuously missing from RAF squadrons, casualties of organizational sluggishness and an entrenched industrial reluctance to embrace change. Squadron leader Desmond Cook, serving with 65 Squadron at Hornchurch, possessed a profound insight into the challenges his pilots would face in the impending conflict. Having personally flown Spitfires against German fighters over France, he recognized that the RAF's operational shortcomings transcended issues of pilot skill or fundamental aircraft design. Rather, they were technical challenges demanding precise technical remedies. As formidable Luftwaffe formations amassed menacingly across the narrow strait for what was codenamed Operation Eagle Attack, Cook resolved to issue an immediate and crucial appeal, an action that would ascertain if British bureaucracy could respond with sufficient alacrity to avert the technological irrelevance of Fighter Command. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Squadron leader Desmond Cook was present within the operations room at RAF Hornchurch on June 10, 1940. intently scrutinizing reconnaissance imagery that chillingly validated his gravest apprehensions. Formidable Luftwaffe formations were visibly concentrating their forces at aerodromes across northern France. The images revealed Stukas, Heinkels, Dorniers, and the feared Messerschmitt fighter escorts. The very aircraft that had held unquestioned aerial supremacy over France. He knew that within a matter of weeks, perhaps even days, these aerial behemoths were poised to descend upon the British Isles. Fighter Command, he realized with dread, would be compelled to engage them with aerial assets suffering from sluggish ascent rates and incapable of attaining the stratospheric levels where crucial aerial engagements would ultimately be decided. Cook's own harrowing experiences, flying Spitfires over Dunkirk, had seared this reality into his memory as he observed powerlessly while German fighters effortlessly outclimbed his squadron at will above 20,000 feet. The underlying mathematics of this aerial disparity were starkly straightforward. His own aircraft required a laborious 11 minutes and 8 seconds to reach an altitude of 20,000 feet, whereas the formidable Messerschmitt Bf-109s could ascend to that identical elevation in less than 9 minutes. In the unforgiving arena of aerial combat, that crucial difference of 2.5 minutes epitomized the critical distinction between successfully engaging hostile bomber formations before they reached their intended targets and appearing on the scene only to witness widespread destruction that could no longer be averted. The vital engineering solution, ironically, was readily available within American manufacturing plants, yet British bureaucracy proceeded at an agonizingly sluggish pace, even as German invasion preparations gained momentum with each passing day. Recognizing the dire urgency, Cook courageously circumvented established protocols and initiated a direct telephone communication with de Havilland Propellers, the authorized British manufacturer for Hamilton Standard's advanced constant speed designs. His request was both pressing and precisely articulated: to immediately equip his squadron's Spitfires with these American-designed propellers, without waiting for formal endorsement or adherence to standard operational procedures. Remarkably, the critical conversion program was initiated within 2 days, commencing under the direct, extraordinary sanction of Air Marshal Dowding himself. De Havilland engineers, demonstrating unparalleled dedication, labored ceaselessly and secured and adapted hangars at Hatfield, undertaking the vital task of transforming Spitfire Mark Is from their outmoded two-pitch propellers to sophisticated, self-regulating, constant velocity systems. Each individual conversion demanded 8 hours of meticulous engineering, a process involving the dismantling of the antiquated propeller assembly, integrating new hydraulic conduits, fine-tuning the intricate governing mechanism, and executing rigorous ground-based evaluations to guarantee flawless functionality. Fighter Command, facing immense pressure, could only release aircraft for a mere 24-hour window, thereby engendering a complex logistical conundrum where squadrons deployed with diminished operational capacity, while their crucial aircraft were subjected to urgent, critical overhauls. The very first converted Spitfire gracefully emerged from the Hatfield facility on June 15, 1940. Cook himself personally undertook the inaugural flight test, ascending from the Verdant airstrip in aircraft serial number K9847. The enhancement became instantly discernible even during the initial takeoff roll. The newly installed propeller seamlessly transitioned to a fine pitch setting, enabling the Merlin power plant to generate its full potential power while simultaneously sustaining the most efficient rotational speed. Whereas his previous aircraft had necessitated a ground run of 320 yards before achieving liftoff, the modified Spitfire achieved airborne status in a mere 225 yards, a remarkable reduction. However, the profound discovery unfolded during the subsequent climb test. Cook advanced the throttle to its full continuous setting and commenced his climb towards 20,000 feet, the critical altitude where Fighter Command anticipated encountering German bomber formations. The constant speed propeller dynamically modulated its settings as atmospheric density diminished, diligently preserving optimal engine revolutions per minute, while autonomously fine-tuning its blade geometry for peak propulsive force. At 5,000 feet, then 10,000 towers, and again at 15,000 towers, the Spitfire ascended with an unprecedented vigor and command that Cook had been entirely unfamiliar with throughout his 3 years of piloting this aircraft model. Reaching 20,000 feet in a staggering 7 minutes and 42 seconds, the aircraft was almost 4 minutes quicker than his prior personal record in an identical, unmodified Spitfire. Cook persisted in his ascent, observing his altimeter indicate elevations that would have been utterly unachievable with the antiquated propeller system. 35,000 feet, then 37,000. Finally at a breathtaking 39,000 feet, where the atmosphere was so rarefied that his exhalations crystallized inside the cockpit. Despite the summer temperatures at ground level, the Spitfire attained its absolute operational zenith. The strategic ramifications of this newfound capability were utterly profound. Fighter Command had previously been formulating defensive strategies predicated on aircraft that contended arduously to reach 32,000 feet and demanded more than 11 minutes to ascend to optimal interception height. Suddenly, RAF fighters were now capable of operating at an additional 7,000 feet of altitude and could attain combat readiness in merely 2/3 of the previous duration. German bomber formations, previously flying at 25,000 feet and hitherto considered secure from meaningful engagement, were now confronted by Spitfires assailing them from a superior position, possessing a distinct, energetic superiority. The advent of constant speed propellers bestowed an undeniable energy advantage upon British fighter aircraft. Upon his landing at Hornchurch, Cook immediately contacted Fighter Command headquarters, delivering a concise yet urgent dispatch. The Spitfire is now an airplane. Request immediate conversion of entire squadron. This powerful statement underscored the profound impact of the new technology. Swiftly, within a mere 72 hours, all 12 operational Spitfires belonging to 65 Squadron underwent retrofitting with these advanced propellers. The pilots' reactions were a mixture of profound astonishment and outright disbelief, as they suddenly experienced an aircraft performance they had previously considered unattainable. Flight Lieutenant Brian Lane, a seasoned combatant from the French campaign, eloquently captured this metamorphosis in his personal combat diary, likening it to an engine replacement that effectively doubled their power. He noted their newfound capability to ascend alongside the formidable Messerschmitt Bf-109 as matching them in altitude. And for the first time since the conflict's commencement, they were no longer operating at a tactical disadvantage. Similar conversion efforts commenced without delay across the entirety of Fighter Command, with dedicated de Havilland engineers tirelessly working 18-hour shifts to equip both Spitfires and Hurricanes before the anticipated German aerial onslaught. The critical numerical superiority and performance enhancements destined to safeguard Britain were rapidly materializing across numerous fighter command airfields. By September of 1940, a remarkable 90% of all Royal Air Force fighters were equipped with constant speed propellers, fundamentally altering the aerial combat landscape. Operational reports from the initial phases of the Battle of Britain vividly documented this dramatic shift in tactical capabilities. The enhanced climb rate of RAF aircraft provided a crucial advantage, enabling fighter command to reach intercept altitudes 2 to 3 minutes faster than German intelligence estimates had predicted. Furthermore, a superior service ceiling, allowing British fighters to operate 4,000 feet above their German counterparts, meant that Spitfires could initiate attacks from advantageous positions where Messerschmitt pilots found it exceedingly difficult to mount an effective counter-response. Perhaps most significantly, the improved fuel efficiency conferred by these propellers extended patrol times by a substantial 45 minutes, empowering RAF squadrons to maintain sustained, vigilant patrols over the primary German approach routes into British airspace, thereby enhancing their defensive posture. The strategic ramifications of these technological advancements stretched far beyond the individual performance metrics of each aircraft. Air Chief Marshal Dowding's sophisticated defensive framework, which was meticulously designed to protect Britain, fundamentally relied on a robust radar early warning system coupled with a rapid scramble response. This integrated approach was crucial for intercepting German formations well before they could reach their designated targets and unleash their destructive payloads. Consequently, every single minute saved in the critical climb to altitude exponentially amplified the overall effectiveness of Fighter Command's inherently limited resources. Pilots who, throughout the summer of 1939, had endured the frustrating experience of watching German aircraft effortlessly escape to higher altitudes, now found themselves in a dramatically altered scenario. They were, for the first time, empowered to dictate precisely when and where to engage the enemy, seizing the initiative in aerial combat. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please leave a comment about where you are from and what you think about the video topic. The most profound manifestation of this transformation was arguably the significant reduction in pilot workload. The introduction of constant speed propellers eliminated the manual pitch adjustment that pilots previously had to perform during the heat of combat. This crucial innovation liberated them to concentrate entirely on complex tactical maneuvers and precise gunnery, rather than being distracted by the demanding intricacies of engine management. In stark contrast, German pilots, who continued to grapple with their manually controlled propellers, found themselves at a severe disadvantage. This disparity became painfully evident when RAF fighters materialized above them, possessing an unprecedented altitude and energy superiority that British aircraft had never previously commanded. As vast formations of Luftwaffe aircraft massed across the English Channel, preparing for their final decisive assault on Britain, Fighter Command stood ready. Their aircraft, now equipped with these vital upgrades, bore little resemblance to the struggling fighters that had contended over France just a few months prior. It was Frank Caldwell's seemingly impossible propeller that had endowed the RAF with the critical performance margin, a margin that ultimately determined whether Britain would endure or succumb to the German invasion. America's subsequent entry into the global conflict following the devastating attack on Pearl Harbor dramatically reshaped Hamilton Standard. What was once a specialized manufacturer was rapidly elevated to the pivotal role of a linchpin in achieving Allied air supremacy. Virtually every major American combat aircraft, including the formidable B-17 Flying Fortress, the versatile B-24 Liberator, the agile P-51 Mustang, the robust P-47 Thunderbolt, and the distinctive P-38 Lightning, required Caldwell's meticulously engineered propellers to fully realize their operational and combat potential. The scale of production demands that ensued was nothing short of staggering, far surpassing anything the peacetime industrial sector could have ever conceived. By the year 1942, Hamilton Standard's order books swelled with contracts for an astonishing 530,135 propeller assemblies. This immense quantity was sufficient not only to equip every single combat aircraft within the entire American arsenal, but also to provide a continuous supply of spares essential for sustained operations across multiple, far-flung theaters of war. The East Hartford factory, which had employed a modest 800 workers in 1932, underwent an exponential expansion, now sprawling across multiple sites and employing a staggering 22,000 individuals who operated 3 shifts around the clock, tirelessly working to meet the insatiable demands of war. Manufacturing partnerships were swiftly forged and extended to prominent companies such as Frigidaire, Nash Kelvinator, and Remington Rand. These erstwhile automobile and appliance manufacturers ingeniously retooled their sophisticated assembly lines, redirecting their considerable industrial capacity towards the urgent production of aircraft propellers. At its peak, monthly output reached an impressive 12,000 complete propeller assemblies, each one necessitating precision machining that demanded incredibly stringent tolerances measured in mere thousandths of an inch to ensure optimal performance and safety. However, this unprecedented scale of mass production inevitably generated immense and unforeseen quality control challenges, issues that relentlessly plagued Caldwell's nights and utterly dominated his waking hours. A troubling trend emerged. Failure rates began to escalate as a burgeoning workforce of inexperienced individuals struggled to master the intricate and complex assembly procedures required for these highly technical components. Subsequent statistical analysis uncovered a disturbing pattern. Propellers manufactured during periods of peak production consistently exhibited higher malfunction rates when compared to units meticulously crafted during the more deliberate, careful pre-war era, a time when highly skilled craftsmen personally inspected every single component, ensuring unparalleled quality. The crisis concerning propeller reliability reached its harrowing zenith over the heavily industrialized city of Schweinfurt on October 14, 1943. A B-17 Flying Fortress, bearing the serial number 4231041 and affectionately nicknamed Hell's Angels by its courageous crew, was desperately struggling for altitude. Its number 3 engine had sustained severe damage from a flak burst directly over the target area. The feathering mechanism, a critical system designed to minimize drag by rotating failed engine propellers parallel to the airstream, initially engaged as expected, allowing the bomber to maintain its formation during the perilous bomb run. However, during the subsequent climb to escape altitude, a critical manufacturing defect within the hydraulic governor caused the feathered propeller to slowly, inexorably rotate back into the airstream. This created massive, uncontrollable drag that violently pulled the B-17 into an unstoppable tragic dive. 9 brave airmen perished when Hell's Angels ultimately crashed into a Bavarian forest. The subsequent and thorough investigation meticulously traced the root cause of this catastrophic failure to contaminated hydraulic fluid. This fluid, under the extreme cold of 30,000 feet, had frozen solid, effectively preventing the governor's intricate system from maintaining the critical blade position. Furthermore, quality control inspectors made a chilling discovery. Similar contamination was found in an additional 47 propellers originating from the very same production batch, all of which had been dispatched to 8th Air Force squadrons, operating from their bases across England. Frank Caldwell, now 54 years old, and shouldering an immense burden of industrial responsibility that no peacetime engineer could have ever conceived, took unequivocal personal accountability for the devastating failure. Demonstrating profound dedication, he flew to England aboard a War Department transport, embarking on a series of direct meetings with bomber crews at various bases across East Anglia. His mission was to gain a precise, first-hand understanding of how his propellers were performing under the brutal and unforgiving conditions of actual combat. These conversations, as expected, were brutally honest and unflinching. Technical Sergeant Michael Romano, a flight engineer serving on a B-24 crew, vividly recounted propeller failures that had, in a mere 2 weeks, cost his squadron 3 valuable aircraft. "The feathering system works fine in training flights over Kansas," Romano observed with poignant frankness. "But over Germany, with flak fragments and battle damage, these complex systems fail when we need them most." Frank Caldwell, upon his return to Connecticut, wasted no time in fundamentally overhauling the propeller's feathering mechanism. His innovative approach involved integrating not only redundant hydraulic circuits, but also robust backup mechanical systems. This ingenious design ensured that the propeller blades could maintain their crucial feathering position, effectively minimizing drag, even in the dire scenario where the primary control systems experienced a complete and catastrophic failure. Furthermore, Caldwell instituted rigorous new quality control protocols. These comprehensive procedures subjected each and every propeller to an exhaustive series of environmental tests, meticulously engineered to replicate the most extreme combat conditions imaginable. These trials included severe temperature cycling, ranging from a frigid 60 degrees below 0 Fahrenheit to a scorching 140 degrees above, simulating the vast thermal fluctuations encountered in high-altitude flight and diverse operational theaters. Additionally, propellers underwent intense vibration testing, deliberately engineered to surpass typical combat stress by an astonishing 75%, guaranteeing resilience under extreme duress. Finally, contamination trials involved intentionally polluting hydraulic fluid with various detrimental substances such as microscopic metal particles, insidious ice crystals, and corrosive chemical residues, which were highly likely to accumulate during prolonged and arduous combat operations. By the pivotal year of 1943, these relentless reliability enhancements had culminated in the creation of what was unequivocally recognized as the most dependable and robust propeller system ever conceived in the annals of aviation history. Empirical evidence from the European theater of operations soon validated these monumental improvements. Combat loss statistics unequivocally demonstrated a dramatic reduction in propeller-related failures, which plummeted to less than a mere 1% of the total mechanical issues encountered. This figure was remarkably lower than the incidence of engine failures, the frequency of landing gear malfunctions, or the prevalence of electrical system breakdowns, highlighting the extraordinary success of Caldwell's redesign. The very feathering system that had initially plagued early designs and caused significant operational headaches now consistently proved to be a lifesaver, routinely preserving both invaluable aircraft and their courageous crews. Detailed operational records from the venerable 8th Air Force meticulously documented hundreds of instances where heavy bombers, despite sustaining critical damage and losing one or even multiple engines deep over hostile German territory, managed to return safely to their bases in England. This remarkable feat was directly attributable to the constant speed propellers, which automatically feathered their blades with precision, effectively eliminating aerodynamic drag, and thereby enabling continued, stable flight on the remaining operational engines, a testament to their newfound reliability. The profound strategic impact of these advanced propeller systems became undeniably evident as American aircraft began to engage German and Japanese fighters in large-scale, intense aerial combat across various theaters. For instance, the iconic P-51 Mustangs, now formidable with Caldwell's meticulously engineered constant speed propellers, consistently demonstrated decisive and often overwhelming performance advantages when pitted against the formidable Messerschmitt Bf 109K models of the Luftwaffe. These American fighters boasted an impressive 30 mph speed advantage and a commanding 5,000 feet of ceiling superiority, critical metrics that empowered Allied pilots to dictate the terms of engagement, choosing precisely when and where to initiate or disengage from combat. Similarly, the robust B-17 Flying Fortresses, equipped with these superior propellers, could cruise an astonishing 50 mph faster than comparable German heavy bombers. Crucially, they operated at an altitude an incredible 8,000 feet higher, effectively placing them well beyond the effective operational ceiling of the vast majority of Luftwaffe interceptors, thereby significantly enhancing their survivability and mission success rates. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The advantages conferred by these sophisticated constant speed propellers proved even more dramatic and pivotal in the expansive and fiercely contested Pacific theater of operations. The formidable P-47 Thunderbolts, initially sometimes dismissed by some critics as being too heavy and cumbersome for agile fighter combat, astonishingly achieved climb rates that were a remarkable 40% superior to those of the nimble Japanese Zero fighters, once they were outfitted with these advanced propeller systems. This significant improvement was largely due to the automatic pitch control mechanism, a technological marvel that allowed American pilots to effortlessly maintain optimal engine performance across the entire flight envelope, particularly during the rapid and often violent altitude changes that were a defining characteristic of aerial engagements in the Pacific. In stark contrast, Japanese pilots were forced to contend with cumbersome manual propeller controls, which not only demanded constant, meticulous attention, but also diverted their critical focus and precious cognitive resources away from the immediate threat of enemy aircraft, often at the very moments when undivided concentration was paramount for survival and victory. General Carl A. Spaatz the esteemed commander of U.S. strategic air forces in Europe, succinctly encapsulated this profound technological transformation in a highly confidential report dispatched to the Pentagon. His assessment was unequivocal. The constant speed propeller has bestowed upon American aircraft truly decisive and unparalleled performance advantages in every theater where we operate. He further emphasized its monumental significance by declaring it as strategically important as radar, long-range navigation, or any other single technology we possess. This powerful statement underscored the propeller's fundamental role not merely as an incremental improvement, but as a foundational element of Allied air superiority, on par with other groundbreaking innovations that redefined modern warfare. A comprehensive statistical analysis meticulously undertaken by the Army Air Forces in the culminating year of 1945 unveiled the staggering impact of these innovations. The findings revealed that constant speed propellers had directly averted an estimated 15,000 Allied aircraft losses. This incredible preservation of assets was achieved through several critical mechanisms. Significantly improved climb performance, which frequently enabled Allied aircraft to escape from aggressive enemy fighters, substantially higher service ceilings, permitting strategic operations at altitudes well above the effective range of most interceptors, the indispensable feathering capability, which routinely allowed for the safe return of aircraft and crews even after catastrophic engine failures, and enhanced fuel efficiency, a crucial factor that drastically reduced the incidence of forced landings caused by fuel exhaustion. Frank Caldwell's pioneering impossible propeller initially met with skepticism and even outright dismissal by various experts who deemed it excessively complex and impractical for the harsh realities of combat operations, had demonstrably proven itself to be far more reliable and robust under actual battle conditions than the simpler fixed-pitch designs it superseded. Ultimately, this very technology, which early detractors had controversially asserted, would inevitably cost American lives due to its perceived complexity, had instead unequivocally saved thousands of airmen, simultaneously furnishing the crucial performance margins and operational flexibility that were absolutely instrumental in making Allied victory a tangible and achievable reality.